Let's start with a review problem. Create a method named contains that takes an array and a value and returns true if the value is in the array and false otherwise. So for this one, we need public, static, and then it returns a boolean, and then contains, and then int brackets array and int value. Then, in order to do this, we must go through every element of the array. For every int I in the array, if I is equal to value, then I return true and quit the method, and otherwise I return false after I've searched everything. And this will work. So contains 457 6 will return false. And then if I replace that with 5, it'll return true. The process of going through every element in an array is called sequential search. And the problem with sequential search is, for example, if we choose the last element in the array, then we have to go through every element. And if we choose an element that's not in the array, then we also have to go through every element because, well, the element's not in the array. So, for example, if we choose an array that has length 100 million, then afterward I populate it. And then afterward I do contains. And then say a value that's not in the array. So let's print A here for a reference of time, and then we can print the result of the contains. And now, although if we only do it once, it may not take that long, like the false follows immediately after the A. If we perform this task 5,000 times, then you'll see the problem. So if we get rid of the print statement because we don't want 5,000 of those, and then just print finished at the end to signal we're done, then what happens is that it's going to take, well, a long time, which is not good. And the reason is because we're searching through every single element of this 100 million size array, which is not good if we perform that 5,000 times. So one way to improve this is to notice that the array is sorted and use something called binary search, which makes you not have to search through every single element of the array. The idea of binary search is the following. Basically, first choose the middle element. If the middle element matches, we are done. Otherwise, if the middle element is too low, then we can search the right half of the array, which gets rid of half the elements, which will reduce our time by a lot. And otherwise, if the middle element is too high, then we can search the left half because it's not going to be higher than that of the array, which also gets rid of half the elements. And what happens here is that now each time we get rid of half the elements, so even on an array of length 100 million, we only need less than 30 steps before we reach our result. Let's run through binary search on this array by hand to give you a better understanding. Check if 56 is in the array. So first, let's label these numbers with indices just so you can see clearly. Although in Java you don't have to do this because you can freely access an array's element in Java just by the index. So we first check the middle element. 35 is less than 56. Now we check the right of it because 56 is too large for 35. It's not going to be less than 35. So then now we check indices 9 through 16. And now we find the middle element, which in this case would be either 12 or 13. Let's just choose 12 because Java rounds down when we divide by 2. So now the index 12, 67 is greater than 56. So now we check indices 9 through 11. And now we check the middle element, which is 51, which is less than 56. Now we check index 11, and then we find that 56 is equal to 56. We are done. And if this number was instead like 57, then 56 would be less than 57. We have nothing more to check, and we're done, and we say 56 isn't in the array. It is very important to remember that when binary searching, our array must be sorted. It can have duplicate elements, but it cannot be out of order. Now we will try to implement binary search. There's two ways of doing this. One is to use a while loop. So we first specify our array. Let's just say that array we just did our binary search on by hand. Then we specify a window to search on. So low equals 0 and high equals arr.length minus 1. So the leftmost element we search is at index 0, and the rightmost element we search is in this case at index 16, or the last element. Then while low is less than high, so basically while the window is not just one element, we do the following. Int mid equals low plus high over 2, which basically that's selecting the middle element, which in this case would be 35 for the first iteration. Then afterward, we check the middle element. So if middle element matches our value, so if array mid, so let's just make it int value equals 56. If array mid equals value, then we just do low equals mid to store the index and then break. And otherwise, if array mid is less than value, that means that our middle element is less than the value, so the value must therefore be in the right half of the array. So then we just do low equals mid plus 1 because, well, the element has to be to the right of mid. Then else, it has to be greater than the value, so then high equals mid minus 1. After this loop is executed, there's two things that could possibly happen. One is that we've hit the value and we break. In that case, the value must be stored at index low in the ARR array. The other possibility is that we've hit low equals high, which means that we've narrowed it down to one element and we only need to check whether that element is the value, and that element is at index low. Either way, we only need to check whether the element at index low is value. So for that to happen, we just do if ARR of low is equal to value, then I do system.out.println true, and else I do system.out.println false. Then we're done. If we plug in 56, it's true, and if we plug in 57, it's false. Here's an exercise. Create a method that uses binary search to search for an element in an int array. So for this one, we only need to make slight modifications to our binary search right here. So first, we obviously need to create a method for this. So public static boolean binary contains int array ARR and int value. Then for this one, let's just take our code for binary search right here, get rid of the value definition. Then for this one, instead of printing, we want to return. So the first thing is, if we find their value, we don't need to still continue in the method. We can just return true. And otherwise, we continue, and if we finish the loop somehow, then if ARR low equals value, I just return true. And else, I just return false. And now, when we print binary contains ARR, 56, it'll print true. And when I do binary contains ARR, 57, it'll print false. Here's another exercise. Do the same thing, except use an array list of integer. So for this one, let's just copy the code over here and paste it right here with slight modifications. So first of all, we need to import array list. So let's just import java.util.star. Then we need to change this method to make it be more like array lists. So .get, because array list doesn't have the brackets for index. And then arr.length should be replaced by arr.size because that's the array list version. So now when we create an array list, and let's just add all the elements of ARR to the list. So list.add I. Then I just print binary contains list, comma, say 56, and it'll print true. And if I change 56 to 57, then it'll print false. Another way to perform binary search is to use recursion. So let's just do create a method, public static boolean recursive contains, and then int array int value. And note that we need the method because recursion needs a method to call itself. And we also need a window, low, high. Then we obviously need a base case in every single recursion. And the base case here is if the window is just one element. So if low is high, then I just return whether ARR low is equal to value. And otherwise, we choose a middle element. Int mid equals low plus high over 2. And then if ARR mid is equal to value, I return true. Otherwise, if ARR mid is less than value, then that means that, well, value is to the right of mid, so then return recursive contains ARR value mid plus 1 high, and else return recursive contains ARR value low mid minus 1. And note we don't need an actual else because return just breaks out of the method. So if ARR mid is not greater than value, then it won't reach this point. And now if we do recursive contains ARR from up here, value 0 ARR.length minus 1, where value is say 56. Then I print it. Then it'll print true, and if it's 57, it'll print false. Here's an example. Create a method that takes a sorted array list and a value and inserts the value in the proper location. So we'll do a method that returns nothing, and we'll name it insert sorted. It'll take in an array list of integer and a value. So we'll find a window for where we can possibly insert it, and we'll shrink the window as we go. And we'll do this using binary search. While low is less than high, int mid equals low plus high over 2. Then if list.get mid is less than value. So what does this mean? Well, this means that the value must be to the right of the mid, which means we don't want to insert it anywhere from mid to the left. So then that means that low equals mid plus 1 is appropriate. Then otherwise, I just do high equals mid. Because, well, what does else mean? That means that list.getMid is greater than or equal to value. That means that value must be inserted either at mid or, well, to the left. So then high equals mid. Then we do list.add. And remember, ArrayList's add function is first the location, which is stored in low, then the value. So now, when we first apply insert sorted to list, which if you recall, is this. And we just add 17 to it. And we print it. Then this is what we'll get. We add 15 to it. Then that's what we'll get. We add 0 to it. That's what we'll get. We add -5 to it. That's what we'll get. However, if we add something like 105 to it, you'll notice that it inserts 105 before 99. Now, why is this? This is because low is at most list.size -1. So then when we insert it at list.size -1, we're actually inserting it at the location of the last element, which pushes the last element to the end, which is not what we want. So actually, we want if list.get list.size -1 is still less than value. So if value is going to be the new largest value in the list, then I just do list.add value, which does it to the end, and then afterward return. And actually we can do this right at the beginning to save some time. And now when we insert 105, it inserts it properly, and the method still works properly if we do it for other numbers. Earlier, we said that the sequential search took a long time when we did it on an array of length 100 million, and we did it 5,000 times. Now you'll see how fast binary search is. So let's just do binary contains instead of just normal contains. And let's comment everything else out. And we'll see how fast this code is. So when we run, it's basically instant. And actually, most of the time is done populating the array. So actually, the binary contains of ARR, 5 done 5,000 times actually barely took any time, as you see right here. So as you see, binary search is way faster than sequential search. And when you have very large inputs, binary search might be a better idea. But make sure that your array is sorted first. So the runtime of sequential search can be very quick if the element is found quickly. But on average, it is linear. And we use big O of n to represent that. And the runtime of binary search is always quick, and on average it is logarithmic, so O of log n. And the reason of this is because each time we get rid of half the elements, so each time we're dividing by 2, so basically there are log base 2, or basically lg of n steps, which means it's lg of n runtime approximately.